Welcome to Module 4 of the Simple Understanding CPIM 9.0 full course. The name of this module is Internal Supply. Internal supply refers to the resources, processes, facilities, materials, people, equipment, information, and planning systems used within an organization to produce products or deliver services. In the previous modules, we studied strategy, sales and operations planning, and demand. Now, we must convert those plans into realistic internal supply decisions. A company may understand what customers want. It may also have an approved demand plan and aggregate supply plan. However, the company still needs to answer several detailed questions. What production environment should we use? Which processes and layouts best support our products? Which products should appear on the master production schedule? Do we have enough capacity to execute the master schedule? Which materials are required? When should those materials be available? How should customer orders be promised? When should final product configurations be completed? How should the company respond when demand, supply, capacity, or priorities change? Module 4 helps us answer these questions. This module connects strategic and aggregate planning with material planning and operational execution. It introduces several of the most important planning tools in CPIM, including the Master Production Schedule, Rough Cut Capacity Planning, Available to Promise, Material Requirements Planning, Capacity Requirements Planning, Capable to Promise, and Final Assembly Scheduling. Many of these concepts include calculations, therefore do not focus only on memorizing definitions. You should understand the relationships among demand, inventory, capacity, materials, lead times, and scheduled production. Poor internal supply planning can create serious problems. A company may promise orders that it cannot produce. It may release materials too early and create unnecessary inventory. It may release materials too late and stop production. It may overload an important work center. It may change the master schedule too frequently and create instability throughout the supply chain. It may also fail to respond effectively when a supplier, machine, employee group, or transportation route becomes unavailable. Effective internal supply planning helps the organization create realistic schedules, protect customer service, use resources efficiently, and respond to change. Don't forget, all videos on the Simple Understanding YouTube channel are translated. You can also listen to dubbed audio in your main language. Before we begin Module 4, remember that the Simple Understanding CPIM 9.0 study materials are available to support your preparation and help you maximize your chance of passing the exam on your first attempt. Bundle 1 is the full learning bundle. It covers all 9 CPIM 9.0 modules and 38 sections. It includes clear explanations, real-world company case studies, and a comprehensive mathematics section with step-by-step formulas and solved examples. Bundle 2 is the MCQs Practice Bundle. It contains more than 6,200 multiple-choice questions, including conceptual, theoretical, scenario-based, and quantitative questions. Every question includes a detailed answer explanation to help you understand the concept and learn from your mistakes. Bundle 3 is the Flashcards Bundle. It contains 1,800 flashcards covering important terms, definitions, formulas, and key CPIM concepts. The flashcards are ideal for quick daily revision and final exam preparation. The download link for all 3 CPIM 9.0 bundles is available in the video description. Use the Learning Bundle to understand the concepts, the MCQs Bundle to test your knowledge, and the Flashcards Bundle to strengthen your memory. Now, let us explore the 8 sections included in Module 4. Module 4 consists of 8 sections. Section A, Functional and Operational Strategies. This section explains how internal operations should support the organization's competitive strategy. We will examine core competencies, resource choices, manufacturing technology, automation, artificial intelligence, make or buy decisions, capacity strategies, and operational trade-offs. Section B, Environments, Types, and Layouts. This section examines different production and service environments. We will study make to stock, assemble to stock, configure to order, make to order, and engineer to order. We will also examine project, job shop, batch, repetitive, assembly line, cellular, continuous flow, fixed position, process, and product layouts. Section C, Creating the Master Schedule. This section explains the role of the Master Production Schedule, commonly known as the MPS. We will examine demand sources, master scheduling levels, planning bills of material, engineering changes, new product introductions, product end-of-life planning, and the creation of an initial master schedule. Section D, Rough Cut Capacity Planning and MPS Validation. This section explains how organizations test whether the master production schedule is realistic. We will study bills of resources, resource profiles, key resources, work center capacity, utilization, efficiency, planned downtime, and methods for identifying capacity overloads. Section E, Using and Maintaining the Master Schedule. This section explains how the organization manages the master schedule after it has been created. We will examine time fences, projected available balances, available to promise, schedule changes, schedule stability, master schedule performance, and the prevention of unnecessary schedule nervousness. Section F, Material Requirements Planning. This section explains how demand for finished products is converted into time-phased requirements for components and raw materials. We will examine MRP inputs, bills of materials, inventory records, BOM explosion, gross requirements, net requirements, planned order receipts, planned order releases, lot sizing, lead time offsetting, action messages, and closed-loop MRP. Section G, Capacity Requirements Planning, Order Promising, and Final Assembly Scheduling. This section explains how detailed capacity requirements are calculated and how organizations make realistic customer commitments. We will examine capacity requirements planning, work center loading, routings, available to promise, capable to promise, final assembly scheduling, and product configuration. Section H, Changes and Supply Disruptions. This section explains how internal supply plans are adjusted when conditions change. We will examine order reprioritization, planning parameter changes, what-if analysis, simulation, analytics, buffers, redundancy, business continuity, and disruption recovery. Let us begin with Section A. Section A, Functional and Operational Strategies. Section A Overview. Operations strategy determines how the organization will use its resources and capabilities to support the business strategy. Operational decisions should not be made independently from customer needs and competitive priorities. The company must decide which capabilities should be developed internally, which technologies should be used, which activities should be outsourced, and how capacity should be managed. In this section, we will study 5 key topics. Topic 1. Aligning operations strategy with competitive priorities. Operations strategy should support the way the organization competes. Common competitive priorities include cost, quality, delivery speed, delivery reliability, flexibility, customization, innovation, availability, responsiveness, sustainability. A company competing mainly through low cost may emphasize standardized products, large production volumes, high equipment utilization, efficient facilities, limited product variety, stable schedules, waste reduction. A company competing through responsiveness may emphasize flexible capacity, short lead times, available inventory, rapid information sharing, cross-trained employees, fast supplier response. A company competing through customization may require modular products, flexible equipment, skilled employees, delayed product differentiation, strong engineering support. The company cannot maximize every priority without trade-offs. For example, maintaining unused capacity can improve responsiveness, but it may increase cost. Producing large batches may reduce setup cost per unit, but it may increase inventory and lead time. The operation strategy should identify which trade-offs are acceptable. Core competencies are the capabilities that provide important customer value and are difficult for competitors to copy. The organization should protect and develop these capabilities. Activities that are strategically important may deserve internal investment even when outsourcing appears less expensive in the short term. Real-world company example: Toyota. The Toyota production system is based on just-in-time and Jidoka. Just-in-time aims to produce what is needed, when it is needed, and in the required quantity. Jidoka focuses on detecting abnormal conditions and preventing defects from continuing through the process. These operating principles support Toyota's priorities for quality, flow, efficiency, problem identification, and waste reduction. Toyota's operational system is therefore connected to the capabilities the organization wants to maintain. CPIM key takeaway: operation strategy should translate competitive priorities into specific capabilities, processes, resource decisions, and performance expectations. Topic 2: Technology choices, ERP, automation, and artificial intelligence. Technology can improve internal supply planning and execution. Common technology choices include enterprise resource planning systems, commonly known as ERP, manufacturing execution systems, commonly known as MES, advanced planning and scheduling systems, commonly known as APICS, warehouse management systems, commonly known as WMAS, automation, robotics, machine learning, artificial intelligence, digital twins, Internet of Things devices. An enterprise resource planning system, commonly known as ERP, integrates information from different organizational functions. It may connect sales orders, inventory, purchasing, production, finance, human resources, engineering, distribution. And manufacturing execution system, commonly known as MES, provides information about activities occurring on the production floor. An advanced planning and scheduling system can evaluate materials, capacity, priorities, and constraints when creating plans. Automation can increase speed, consistency, accuracy, safety, and productivity. However, technology should not be selected only because it is modern. The company should evaluate the business problem, expected benefits, total cost, required skills, data quality, integration, cybersecurity, maintenance, implementation risk, scalability, employee adoption. Automating a poor process may allow the organization to perform the wrong activity faster. The process should first be understood and improved. Artificial intelligence can identify patterns and evaluate alternatives. However, its output still depends on data quality, model design, governance, and human judgment. Real-world company example: Siemens. Siemens uses the concept of a digital enterprise to connect product design, production planning, engineering, automation, execution, and service. Digital twins can be used to simulate and validate products and manufacturing processes before physical implementation. This can help organizations identify layout, equipment, material flow, and process problems earlier. The important lesson is that technology creates the greatest value when information and processes are integrated rather than isolated. CPIM key takeaway: technology should support a defined operational objective. The most advanced system is not valuable when the organization lacks reliable data, appropriate processes, skilled users, or clear decision responsibilities. Topic 3: Make or buy analysis. Make or buy analysis determines whether an activity, component, product, or service should be performed internally or purchased from an external supplier. The decision should not be based only on the supplier's quoted price. Important considerations include internal capacity, supplier capacity, direct cost, indirect cost, transportation, inventory, quality, lead time, intellectual property, technology, flexibility, risk, supplier reliability, required investment, strategic importance, management attention. The organization may choose to produce internally when the activity is a core competency. Intellectual property must be protected. Quality requirements are difficult to control externally. internal capacity is available, the activity provides strategic differentiation. The organization may buy externally when a supplier has specialized expertise, internal capacity is limited, investment requirements are high, demand is temporary or uncertain, external production provides greater flexibility. Total cost should include more than purchase price. For example, an external supplier may offer a component for $8, while the estimated internal manufacturing cost is $9. At first, buying appears better. However, the external option may also require $1 for transportation, 50 cents for inspection, 75 cents for additional inventory, and 50 cents for supplier management and risk. The effective external cost becomes $10.75. The company must also consider whether internal fixed costs will actually disappear after outsourcing. If the facility and management costs remain, the apparent saving may not be real. Real-world company example: Nike. Nike works with contract manufacturing suppliers for much of its footwear and apparel production. This allows Nike to use specialized external manufacturing capabilities while concentrating on areas such as product development, brand management, design, innovation, and customer relationships. However, using external factories does not remove Nike's responsibility for supplier performance. The company still requires supplier standards, monitoring, collaboration, quality controls, labor expectations, and long-term relationship management. CPIM key takeaway: make or buy is a strategic total cost and risk decision. The lowest visible price is not automatically the best choice. Topic 4. Capacity strategies. Capacity is the capability of a resource to produce output during a period. Capacity decisions may involve employees, machines, production lines, facilities, suppliers, warehouses, transportation, technology. Several capacity strategies can be used. Lead strategy. A lead strategy adds capacity before demand is expected to require it. This can improve responsiveness and protect customer service. However, capacity may remain unused when demand does not grow as expected. Lag strategy. A lag strategy adds capacity only after demand has clearly increased. This reduces the risk of unused resources. However, the organization may experience shortages, delays, overtime, and lost sales before capacity is added. Chase strategy. A chase strategy changes capacity to follow demand. The company may adjust labor, shifts, overtime, suppliers, or subcontracting. This reduces inventory but can create instability and higher adjustment costs. Level strategy. A level strategy maintains relatively stable capacity and output. Inventory or backlog absorbs changes in demand. This can stabilize employees and production, but may create inventory or customer delays. Hybrid strategy. A hybrid strategy combines several methods. The organization may maintain stable base capacity while using overtime, temporary employees, inventory, or subcontractors during peaks. Subcontracting can provide temporary capacity. However, it may introduce higher cost, quality risk, coordination problems, and dependency. Capacity strategy should reflect demand uncertainty, product lifecycle, customer lead time expectations, cost, skills, investment requirements, flexibility, risk. Real-world company example: Boeing. When future aircraft demand requires additional output, Boeing may need to expand production capacity through facilities, equipment, production lines, employees, suppliers, and training. Adding another production line before the full demand is realized represents a lead capacity decision. The investment may protect future delivery capability, but it also requires confidence that demand and supplier readiness will support the added capacity. CPIM key takeaway. Capacity strategy determines when and how resources are added or adjusted. Every approach creates trade-offs among cost, risk, utilization, inventory, customer service, and flexibility. Topic 5. Operational trade-offs and resource decisions. Operational decisions are interconnected. Improving one measure may damage another. For example, larger production lots may reduce setup cost but increase inventory. Higher equipment utilization may increase output but create longer queues. Additional safety stock may improve availability but increase carrying cost. More product variety may attract customers but increase complexity. Faster transportation may improve service but increase cost and emissions. The organization should evaluate the total system. A local decision should not be considered successful when it creates a larger problem elsewhere. Important resource decisions include workforce size, employee skills, cross-training, equipment selection, facility capacity, maintenance support, automation, inventory buffers, supplier support, information systems. The organization should also consider policies and constraints. These may include safety regulations, environmental requirements, intellectual property protection, quality standards, labor agreements, financial limits, technology standards, cybersecurity requirements. Operational strategies should be reviewed when customer demand, products, technology, regulation, or competition changes. A process that supported a mature product may not support a newly introduced customized product. Real-world company example: Amazon. Amazon combines employees, fulfillment facilities, software, forecasting, robotics, inventory placement, and transportation capabilities. Its robotic systems are intended to support employees while improving fulfillment speed, accuracy, safety, and productivity. The lesson is not that every organization should use the same level of automation. The lesson is that Amazon's resource choices are connected to its strategic requirements for availability, speed, reliability, and scale. CPIM Key Takeaway: operational decisions should be evaluated through total system performance. High utilization or low unit cost is not a good result when customer service, quality, flow, safety, or flexibility is damaged. Let's summarize the 5 key lessons from Section A. First, align operations with competitive priorities. Internal operations must support how the company competes, whether through cost, quality, speed, reliability, customization, innovation, or sustainability. Second, choose technology for a clear business purpose. ERP, MES, automation, robotics, AI, digital twins, and planning systems are useful only when they solve real operational problems and are supported by accurate data. Third, make smart make or buy decisions. The choice to produce internally or buy externally should consider total cost, capacity, quality, lead time, intellectual property, risk, and strategic importance, not only the supplier's quoted price. Fourth, select the right capacity strategy. Lead, lag, chase, level, hybrid, and subcontracting strategies each create trade-offs between cost, utilization, flexibility, inventory, and customer service. Finally, evaluate operational trade-offs as a total system. High utilization, low unit cost, or fast transportation may look good locally, but can damage service, quality, flow, safety, or flexibility. Section A shows that internal supply begins with strategy. Operations must build the right capabilities, not just run activities efficiently. Section B: environments, types, and layouts. Section B overview. Products and services can be produced in different environments. The correct environment depends on demand volume, product variety, customization, customer lead time expectations, technology, and product lifecycle stage. Process and layout decisions determine how people, equipment, materials, information, and customers move through the operation. In this section, we will study 5 key topics. Topic 1. The product process matrix and manufacturing process types. The product process matrix connects product characteristics with suitable processes. Products with low volume and high variety normally require flexible processes. Products with high volume and low variety normally use more standardized and repetitive processes. Common manufacturing process types include project. A project creates a unique product or result. Examples include major construction, large infrastructure, and specialized installations. Resources normally move to the product. Job shop. A job shop produces low volumes of highly varied products. Products may follow different routes through specialized departments. This environment requires skilled employees and flexible equipment. Batch production. Batch production creates products in groups or lots. Equipment may be changed over between batches. This provides more volume than a job shop while maintaining some variety. Repetitive or assembly line production. Repetitive production creates standardized products through a defined sequence. It normally supports higher volume and lower variety. Continuous flow processes. Continuous flow processes operate with highly standardized and uninterrupted material movement. Examples include chemicals, oil refining, paper, and some food processes. Mass customization. Mass customization attempts to provide customer variety while maintaining many efficiencies of high-volume production. This may require modular design, flexible automation, postponement, and strong information systems. The selected process should match volume and variety. Using a highly repetitive line for frequently changing customized products may create excessive changeovers and disruption. Using a flexible job shop for a very high-volume standardized product may create high cost and inconsistent flow. Real-world company example. Boeing. Commercial airplanes are large, complex, low-volume products compared with consumer goods. Their production requires specialized work, major assemblies, technical skills, extensive supplier coordination, and long production cycles. This environment is very different from producing millions of identical packaged products. Boeing's manufacturing system must therefore support complexity, quality, engineering control, and large-scale assembly. CPIM key takeaway. The production process should match product volume, variety, customization, complexity, and lifecycle requirements. Topic 2. MTS, ATO, CTO, MTO, and ETO environments. The production environment determines when production begins compared with the customer order. Make to stock. In a make-to-stock or MTS environment, products are produced before receiving a specific customer order. Demand is normally forecast. Customer delivery can be fast because finished goods are available. However, forecast errors may create shortages or excess inventory. Assemble to order. In an assemble-to-order or ATO environment, standard components or subassemblies are produced before the order. Final assembly begins after the customer selects the required configuration. This reduces finished goods inventory while allowing some customization. Configure to order. Configure to order allows the customer to select from predefined options. The final product is configured from standard modules. The organization must control which combinations are technically and operationally valid. Make to order. In a make-to-order or MTO environment, production begins after the customer order is received. Finished goods inventory is reduced, but customer lead time is longer. Engineer to order. In an engineer-to-order or ETO environment, engineering and design activities begin after receiving the customer requirement. Products are highly customized and normally have longer lead times. The push-pull boundary separates activities performed based on forecasts from activities performed in response to actual customer demand. Moving the boundary closer to the customer can increase responsiveness and reduce finished goods inventory. However, the organization must still provide an acceptable customer lead time. Real-world company example. Dell. Dell became widely associated with building computer systems after receiving customer orders. Customers could select from defined components such as processors, memory, storage, and other options. Standard components could be available before the order, while final configuration and assembly responded to the customer's selection. This illustrates assemble-to-order or configure-to-order principles. CPIM key takeaway. The production environment determines the relationship among forecasts, customer orders, inventory, configuration, and lead time. Topic 3. Manufacturing layouts. A layout determines the physical arrangement of resources. Common layouts include fixed position layout. The product remains in one location while employees, tools, equipment, and materials move to it. This is suitable for very large or difficult-to-move products. Process or functional layout. Similar resources are grouped together. For example, all drilling machines may be placed in one area and all painting operations in another. Different products can follow different routes. This supports variety but may increase movement, queues, and scheduling complexity. Product layout. Resources are arranged according to the sequence required to produce a product. This supports high volume and smooth flow. However, it may be less flexible when products or volumes change. Cellular layout. Different resources are placed together in a cell to produce a family of similar products. Cells can reduce movement, work in process inventory, and lead time. Assembly line layout. Workstations are arranged according to a repeated assembly sequence. The line must be balanced so that work is distributed appropriately among stations. The best layout depends on volume, variety, product size, routing, technology, safety, flexibility, material movement, customer involvement. The organization should evaluate total flow rather than only equipment location. A low-cost machine location may create expensive movement, waiting, handling, and inventory. Real-world company example. Toyota. Automotive assembly uses a product-focused sequence in which vehicles move through connected production activities. Work content, materials, employees, quality checks, and equipment must be coordinated with the pace of the line. The layout supports flow and volume, but it requires disciplined planning and rapid response when an abnormal condition occurs. CPIM key takeaway. Layout should support safe and efficient movement of products, materials, information, employees, and customers. Topic 4. Service environments and customer contact. Service operations differ according to the level of customer contact. A high-contact service allows customers to interact directly with the operation. A low-contact service performs more activities away from the customer. Service activities may be divided into front room. The front room contains activities visible to or involving the customer. Examples include reception, ordering, consultation, payment, customer support. Back room contains activities performed away from the customer. Examples include preparation, data processing, inventory storage, maintenance, administrative work. Higher customer contact may create opportunities for personalization and sales. However, it may reduce production efficiency because customer requests are variable. Backroom activities can often be standardized and controlled more easily. Service layouts should consider customer flow, waiting time, employee movement, accessibility, safety, visibility, privacy, information flow, inventory placement, customer experience. Capacity is also perishable in services. An unused hotel room or appointment time normally cannot be stored for future sale. Service organizations must therefore coordinate demand and capacity carefully. Real-world company example. Starbucks. A Starbucks store combines front room and back room activities. Customers place orders, communicate with employees, make payments, and receive beverages in the front room environment. Preparation, inventory storage, cleaning, equipment support, and some administrative tasks occur behind the customer-facing activity. The store layout must support customer experience while allowing employees to prepare orders safely and efficiently. CPIM key takeaway. Service design must balance customer contact, personalization, flow, waiting time, employee productivity, and operational control. Topic 5. Aligning processes and layouts with the product lifecycle. Products normally move through lifecycle stages. These include introduction, growth, maturity, decline, and end of life. During introduction, demand may be uncertain and the design may change frequently. Flexible equipment and layouts may be more suitable. During growth, the organization may need to increase capacity and improve process stability. During maturity, demand may become more predictable. The organization may emphasize efficiency, automation, standardization, and cost reduction. During decline, capacity and inventory may need to be reduced. The company may combine production with other products or move it to a more flexible resource. Layout decisions should not be considered permanent. The company should periodically examine whether the current process still supports product volume, variety, technology, customer requirements, employee safety, material movement, and future products. Digital simulation can help evaluate changes before physical implementation. A digital twin may represent facilities, equipment, material flow, people, and processes. The company can test different layouts and identify problems before moving equipment or starting production. Real-world company example: BMW. BMW uses virtual factory planning and digital twins to simulate layouts, logistics, robotics, and production activities before physical changes are made. This is especially useful when introducing new or updated vehicle models. The company can evaluate whether a new product will fit existing production processes and identify possible conflicts before the launch. CPIM key takeaway: processes and layouts should change as product volume, variety, technology, and life cycle requirements change. Let's summarize the 5 key lessons from Section B. First, match the process to product volume and variety. Projects, job shops, batch production, repetitive production, assembly lines, mass customization, and continuous flow each fit different product characteristics. Second, understand the production environment. Make to stock, assemble to order, configure to order, make to order, and engineer to order define when work begins compared with the customer order. Third, choose the right layout. Fixed position, process, product, cellular, and assembly line layouts affect material movement, waiting time, flexibility, safety, and productivity. Fourth, design service operations around customer contact. Front room and back room activities must balance customer experience, personalization, waiting time, employee productivity, and operational control. Finally, adjust processes as products move through the life cycle. Introduction, growth, maturity, decline, and end-of-life stages may require different levels of flexibility, automation, capacity, and inventory control. Section B shows that there is no single best production environment or layout. The right choice depends on volume, variety, customization, lead time, customer contact, and product lifecycle stage. Section C. Creating the Master Schedule. Section C Overview. The Master Production Schedule, commonly called the MPS, states which independent demand items the organization plans to complete, in what quantities, and during which periods. The MPS connects S&OP with material and capacity planning. It must be realistic, time-phased, and consistent with the organization's resources and priorities. In this section, we will study 5 key topics. Topic 1. The role of master scheduling and sources of demand. The master schedule is located between aggregate planning and detailed material planning. The S&OP normally defines broad volumes by product family. The MPS converts part of this aggregate plan into specific end items, options, modules, or subassemblies. MRP then uses the MPS to calculate component and material requirements. The master scheduler should consider all valid demand sources. These may include forecasts, customer orders, interplant orders, distribution requirements, service parts, samples, testing, promotions, product introductions, safety stock requirements, the scheduler should avoid double counting. For example, customer orders may already be included within the forecast. The treatment of forecasts and customer orders may change according to the demand time fence. The master schedule should cover at least the cumulative lead time required to obtain materials and complete production. A horizon that is too short may fail to provide enough time to release long lead materials. The MPS is not simply a sales forecast. A forecast states what the organization expects customers to request. The MPS states what the organization plans to supply. The MPS must therefore consider inventory, capacity, materials, priorities, and management decisions. Real-world company example: Procter & Gamble. P&G manages many brands, product families, package sizes, and individual items. Its aggregate business plan cannot directly schedule every specific product. Master scheduling provides the connection between family-level plans and the specific items that materials, production, and distribution must support. CPIM key takeaway: the forecast represents expected demand. The MPS represents the organization's authorized production plan for selected independent demand items. Topic 2. Selecting the correct master scheduling level. The level where the MPS is created depends on the production environment. In a make-to-stock environment, the MPS is usually created for finished goods. For example, the schedule may state how many finished washing machines will be completed each week. In an assemble-to-order environment, the MPS may be created for major subassemblies or modules. The final product configuration is completed after receiving the customer order. In a make-to-order environment, the MPS may be based on customer orders or common components. In an engineer-to-order environment, major project milestones, engineering deliverables, or critical resources may be scheduled. Selecting the wrong level can create problems. If a company offers thousands of configurations, scheduling every finished configuration before receiving customer orders may create excessive complexity and inventory. Scheduling only very low-level raw materials may not provide enough visibility into customer-facing output. The MPS should provide effective customer order promising, useful capacity planning, manageable detail, clear connection to demand, control of important resources, and appropriate product flexibility. The organization should also distinguish between independent and dependent demand. Items at the MPS level usually have independent demand. Components below that level usually have dependent demand calculated by MRP. Real-world company example: Dell. In a configure-to-order computer environment, master scheduling every possible finished computer configuration would be difficult. A more effective approach is to schedule important modules and components, such as base systems, processors, memory categories, and storage options. The final configuration can then respond to the customer order. CPIM key takeaway: the MPS should be created at the level that provides effective demand control, capacity validation, material planning, and customer order promising. Topic 3. Planning bills of material. A planning bill of material is an artificial grouping used for planning. It may not represent a product that is physically assembled or sold. Planning bills can help the organization forecast and schedule product families, options, and modules. Suppose a company sells a family of 1,000 computers. Historical information indicates 60% require standard memory, 30% require high memory, 10% require premium memory. A planning bill can convert the family forecast into expected option demand. Standard memory demand, 1,000 multiplied by 60% equals 600. High memory demand, 1,000 multiplied by 30% equals 300. Premium memory demand, 1,000 multiplied by 10% equals 100. Planning bills may be modular bills, common parts bills, option bills, or super bills. The percentages should be reviewed regularly. Customer preferences may change. A percentage that was correct last year may create shortages or excess inventory today. Planning bills support two-level or multi-level master scheduling. At one level, the organization may schedule the total family plan. At another level, it may schedule modules or options. The combined schedule should remain consistent with the family plan. Real-world company example: an automotive company such as Toyota. A vehicle family may include several engines, transmissions, interiors, colors, and option packages. Planning every exact finished configuration far in advance would create enormous complexity. Planning bills can estimate the expected demand for important options, while actual customer orders provide more specific information closer to production. CPIM Key Takeaway: planning bills translate family-level plans into expected requirements for options, modules, and common components. Topic 4. Engineering changes and new product introduction schedules. Engineering changes may affect product design, materials, components, bills of materials, routings, tools, quality requirements, suppliers, inventory, work instructions. The organization must determine the effective date of the change. A change may be introduced using immediate effectivity, date effectivity, lot number effectivity, serial number effectivity, phase in and phase out. The company should decide what will happen to existing inventory. Possible actions include use the old material until exhausted, rework existing inventory, return material to the supplier, use it for service parts, scrap it. New product introduction, commonly known as NPI, also requires coordinated scheduling. The schedule may include design completion, prototype production, testing, regulatory approval, supplier qualification, tooling, employee training, pilot production, inventory preparation, commercial launch. Design for Manufacturing and Assembly, or DFMA, aims to make products easier and less costly to produce and assemble. Modular design can also improve flexibility and simplify product configuration. An NPI schedule should consider both demand and supply constraints. Launching before the product and supply network are ready may create quality and service failures. Launching too late may cause the organization to miss a market opportunity. Real-world company example: BMW. BMW uses virtual factory models to simulate how new vehicle designs will move through production facilities. Layouts, equipment, logistics, robotics, and employee activities can be evaluated before physical production begins. This helps connect new product design with manufacturing readiness and launch scheduling. CPIM Key Takeaway: engineering changes and new product introductions must be synchronized with materials, suppliers, capacity, inventory, processes, and customer commitments. Topic 5. Product End-of-Life Planning and the Initial MPS. End-of-life planning determines how production will be reduced and stopped. The organization should consider final customer orders, service part requirements, warranty obligations, remaining materials, supplier minimum order quantities, supplier lifetime buy requirements, obsolete inventory, replacement products, customer communication. Suppose a supplier announces that an electronic component will be discontinued. The company expects to require 2,000 units for final production and 500 units for future service. Current usable inventory is 600 units. The lifetime buy requirement is 2,000 plus 500 minus 600. The result is 1,900. However, the organization should also consider forecast risk, failure rates, scrap, yield, storage life, minimum supplier order quantities. The initial MPS can be tested using projected available balance. A simplified formula is projected available balance equals previous projected available balance plus MPS quantity minus demand used for the period. Assume beginning inventory equals 40 units. Week 1 forecast equals 25. Week 1 customer orders equal 30. Week 1 MPS quantity equals 0. If the greater of forecast or orders is used, Week 1 demand equals 30. Week 1 projected available balance equals 40 plus 0 minus 30. The result is 10 units. In Week 2, forecast equals 25, customer orders equal 15, MPS quantity equals 50, demand used equals 25. Week 2 projected available balance equals 10 plus 50 minus 25. The result is 35 units. The schedule should prevent projected inventory from becoming unacceptable while avoiding unnecessary production. Real-world company example. Apple. When an organization introduces a new product generation, it must manage the transition from the older version. Producing too many old products may create obsolete inventory. Reducing production too early may create shortages before the new product becomes available. Product transition planning must coordinate demand, inventory, supplier commitments, production, and launch timing. CPIM key takeaway. The master schedule should coordinate current demand, product introductions, engineering changes, and end-of-life requirements without creating shortages or unnecessary inventory. Let's summarize the 5 key lessons from Section C. First, understand the role of the MPS. The master production schedule translates the S&OP plan into specific independent demand items, quantities, and timing. Second, select the correct master scheduling level. In make-to-stock, the MPS may be finished goods. In assemble-to-order or configure-to-order, it may be modules, options, or subassemblies. Third, use planning bills of materials. Planning bills help convert family-level forecasts into expected requirements for options, modules, and common components. Fourth, coordinate engineering changes and new product introductions. Product changes must be synchronized with materials, suppliers, routings, inventory, capacity, testing, and customer commitments. Finally, manage product end-of-life carefully. Final orders, service parts, warranty needs, supplier commitments, obsolete inventory, and replacement products must be included in the initial master schedule. Section C shows that the MPS is not just a forecast. It is the authorized supply plan that connects strategy, demand, inventory, materials, capacity, and execution. Section D. Rough cut capacity planning and MPS validation. Section D overview. Rough cut capacity planning, commonly known as RCCP, checks whether the organization has enough critical capacity to execute the proposed master production schedule. It focuses on major or constrained resources rather than every detailed operation. RCCP should identify unrealistic schedules before they are released to MRP and detailed execution. In this section, we will study 5 key topics. Topic 1. The purpose of RCCP. The MPS describes what the organization plans to complete. RCCP determines whether important resources can support that plan. Key resources may include a specialized machine, a production line, a highly skilled employee group, a testing facility, a paint operation, a clean room, a supplier with limited capacity, an engineering team. RCCP is less detailed than capacity requirements planning. It normally uses the MPS, bills of resources, planning factors, historical resource usage, resource profiles. The objective is not to create a detailed work center schedule. The objective is to determine whether the MPS is broadly realistic. When required capacity exceeds available capacity, the organization may change the MPS, add overtime, move work to another resource, use an alternative resource, subcontract, change the product mix, build inventory earlier, delay demand, add capacity. Ignoring the overload does not solve it. A plan should not be approved simply because the spreadsheet is complete. Real-world company example. Boeing. Before increasing an aircraft production schedule, Boeing must consider whether major assembly lines, skilled employees, suppliers, tooling, testing activities, and quality systems can support the higher rate. A demand plan for more aircraft is not enough. Critical resources must be validated before the production commitment becomes realistic. CIPM key takeaway. RCCP tests whether critical resources can support the master schedule before detailed material and capacity plans are created. Topic 2. The Bill of Resources Method. A bill of resources identifies the key capacity required to produce one unit of an MPS item. Suppose product A requires 1.5 hours at Work Center X. Product B requires 2 hours at Work Center X. The MPS requires 100 units of product A, 60 units of product B. Capacity required for product A is 100 multiplied by 1.5 hours. The result is 150 hours. Capacity required for product B is 60 multiplied by 2 hours. The result is 120 hours. Total required capacity is 150 plus 120. The result is 270. If Work Center X has only 250 hours available, the overload is 270 minus 250. The result is 20 hours. The organization must decide how to manage the 20-hour overload. Possible actions include overtime, moving work to another resource, changing the MPS timing, reducing the planned quantity, improving productivity, subcontracting. The Bill of Resources should include important resources, not every small activity. It should also be updated when processes, products, equipment, routings, or standard times change. Real-world company example. Toyota. A vehicle production plan requires capacity from several key areas, such as body production, painting, engine supply, final assembly, and inspection. If the paint operation cannot support the planned mix, unused capacity in another department will not remove the constraint. A Bill of Resources approach helps identify which major resources are required by the proposed schedule. CIPM Key Takeaway. The Bill of Resources converts MPS quantities into capacity requirements for critical resources. Topic 3. Capacity planning using overall factors and resource profiles. Capacity planning using overall factors estimates capacity using historical relationships. Suppose historical information indicates that every unit of a product requires an average of 4 total labor hours. The MPS requires 500 units. Estimated labor requirement equals 500 multiplied by 4 hours. The result is 2,000 labor hours. If historical percentages show that 30% of the hours occur in machining, 50% occur in assembly, 20% occur in testing, then 30% of the hours occur in machining, which is 2,000 multiplied by 30%, equals 600 hours. Assembly requires 2,000 multiplied by 50%, equals 1,000 hours. Testing requires 2,000 multiplied by 20%, equals 400 hours. This method is relatively simple. However, it assumes that historical proportions remain valid. A change in product mix, process, technology, or routing may make the result inaccurate. Resource profiles provide more detailed time-phased information. They identify not only how much capacity is required, but also when it is required. For example, machining may occur 2 weeks before final assembly. Testing may occur during the completion week. Time phasing helps identify capacity problems that a total period calculation may hide. Real-world company example. BMW. BMW's virtual factory combines production, equipment, logistics, building, and vehicle information. Production planners can evaluate how future product launches will impact resources and layouts before physical implementation. This illustrates the value of using more detailed and time-sensitive resource information rather than relying only on historical total averages. CIPM Key Takeaway. RCCP offers a quick capacity estimate, while resource profiles provide more detailed time-phased information. Topic 4. Utilization, efficiency, and rated capacity. Available capacity is not always equal to the number of calendar hours. Several measures help evaluate capacity. Utilization. Utilization measures how much of the available time was actually used. The formula is utilization equals actual hours worked divided by available hours multiplied by 100. Suppose a work center was available for 400 hours but operated for 340 hours. Utilization equals 340 divided by 400 multiplied by 100. The result is 85%. Efficiency. Efficiency compares standard output time with actual operating time. The formula is efficiency equals standard hours produced divided by actual hours worked multiplied by 100. Suppose the work center produced 306 standard hours of output during 340 actual operating hours. Efficiency equals 306 divided by 340 multiplied by 100. The result is 90%. Rated capacity. A common formula is rated capacity equals available time multiplied by utilization multiplied by efficiency. Using 400 available hours, 85% utilization, and 90% efficiency, rated capacity equals 400 multiplied by 0.85 multiplied by 0.90. The result is 306 standard hours. Suppose RCCP shows a requirement of 330 standard hours. The overload is 330 minus 306. The result is 24 standard hours. Management should not assume that 400 calendar hours provide 400 productive standard hours. Real-world company example, Amazon. An Amazon fulfillment operation may have a large physical facility, but usable capacity depends on employees, equipment availability, system performance, inventory positioning, process efficiency, and demand timing. The building's theoretical maximum does not automatically represent the capacity available for customer orders. CPIM key takeaway. Capacity plans should use realistic capacity after considering utilization, efficiency, downtime, and operational constraints. Topic 5. Planned downtime and MPS validation. Maintenance, training, holidays, changeovers, quality activities, and planned upgrades reduce available capacity. These events should be included before approving the MPS. Suppose a work center normally provides 5 machines, 8 hours per shift, 2 shifts per day, 5 days per week. Theoretical weekly capacity is 5 multiplied by 8 multiplied by 2 multiplied by 5. The result is 400 machine hours. However, scheduled maintenance requires 40 hours. Training requires 16 hours. Adjusted available capacity becomes 400 minus 40 minus 16. The result is 334 hours. If the company ignores this downtime, the MPS may appear feasible even though execution will fail. MPS validation should examine critical resource overloads, material availability, maintenance schedules, labor availability, tooling, supplier capacity, product mix, quality requirements, new product constraints. When the schedule is not feasible, management should make a real decision. Possible decisions include changing timing, changing quantity, adding capacity, changing the mix, adjusting demand, or using alternative resources. The schedule should then be validated again. Real-world company example, Boeing. Aircraft production requires extensive maintenance, inspection, quality verification, tooling, and employee training. Capacity planning that considers only assembly hours and ignores these requirements would overstate the achievable production rate. CPIM key takeaway. The MPS should be approved only after realistic capacity, maintenance, downtime, materials, and constraints have been considered. Let's summarize the 5 key lessons from Section D. First, use RCCP to test the MPS. Rough-cut capacity planning checks whether critical resources can support the proposed master schedule before the plan is released to detailed execution. Second, convert MPS quantities into capacity needs. Bills of resources show how much key resource capacity is required for each MPS item. Third, use overall factors and resource profiles. Overall factors provide quick capacity estimates, while resource profiles show when capacity is needed across time. Fourth, calculate realistic rated capacity. Capacity must consider available time, utilization, efficiency, downtime, maintenance, training, and operational constraints. Finally, validate the MPS before approval. A master schedule should not be approved unless critical resources, materials, planned downtime,
labor, suppliers, tooling, quality requirements, and product mix are realistic. Section D shows that a schedule is not feasible just because demand exists. Capacity must prove that the organization can actually execute the plan.
Quick reminder, if you're finding this helpful, don't forget to like, subscribe, and share with anyone who may benefit. Your support really makes a difference. Let's get back to it.
Section E. Using and maintaining the master schedule. Section E. Overview. The master schedule must be controlled after it is created. Demand, supply, inventory, and customer priorities may change. However, changing the MPS too frequently can create instability throughout the organization and supplier network. The master scheduler must balance responsiveness with schedule stability. In this section, we will study 5 key topics. Topic 1. Time fences and planning zones. Time fences establish boundaries for controlling schedule changes. Demand time fence. The demand time fence, commonly called DTF, is the point inside which changes are highly restricted. Within this zone, the organization may rely mainly on actual customer orders because there may not be enough time to respond to new forecast demand. Planning time fence. The planning time fence, commonly called PTF, normally extends beyond the demand time fence. Inside the PTF, changes may require analysis and approval because materials or capacity may already be committed. The planning horizon may be divided into zones. Frozen zone. Changes are prohibited or require senior approval. Production and materials may already be committed. Slushy zone. Changes are possible but should be evaluated carefully. Liquid zone. Changes can be made more easily because there is more time to adjust materials and capacity. The time fence length should reflect cumulative lead time, supplier commitments, capacity flexibility, product complexity, customer expectations. Time fences should not prevent the organization from responding to a genuine emergency. However, they should prevent unnecessary changes that create widespread disruption. Real-world company example. Toyota. A stable production schedule helps Toyota and its suppliers coordinate materials, employees, equipment, and deliveries. Frequent last-minute changes can create shortages, excess materials, overtime, and transportation problems across the network. Time fences provide a structured method for evaluating which schedule changes are still practical. CPIM key takeaway. Time fences protect schedule stability while defining when and how changes may be approved. Topic 2. Projected available balance. Projected available balance, commonly called PAB, estimates the inventory expected to remain after demand and scheduled production are considered. A simplified formula is projected available balance for the current period equals previous PAB plus current MPS quantity minus demand used in the current period. Demand treatment may depend on the time fence. Inside the demand time fence, customer orders are commonly used. Outside the demand time fence, the greater of the forecast or orders may be used. Consider this example. Beginning inventory is 30 units. Week 1. Forecast equals 20. Customer orders equal 25. MPS quantity equals 40. Assume the greater of forecast or orders is used. Demand equals 25. PAB equals 30 plus 40 minus 25. The result is 45 units. Week 2, forecast equals 30. Customer orders equal 18, MPS quantity equals 0. Demand equals 30. PAB equals 45 plus 0 minus 30. The result is 15 units. Week 3. Forecast equals 35, customer orders equal 20, MPS quantity equals 50. Demand equals 35. PAB equals 15 plus 50 minus 35.
The result is 30 units. The master scheduler monitors the PAB to identify potential shortages or excessive inventory. An MPS receipt should normally be scheduled before the balance becomes unacceptable. Real-world company example. Dell. In a computer assembly environment, the planner must understand how scheduled production, customer orders, and expected demand will affect available systems and modules. A projected shortage can prevent the company from meeting customer orders. Excessive scheduled production can create unnecessary inventory and technology obsolescence risk. CPIM key takeaway. PAB helps the scheduler determine whether the master schedule will provide sufficient inventory to support demand. Topic 3. Available to promise. Available to promise, commonly known as ATP, represents the uncommitted portion of inventory and scheduled production that can be promised to customers. ATP is based on customer orders rather than forecasts. A common discrete ATP calculation for the first MPS receipt is beginning inventory plus the first MPS quantity minus customer orders until the period before the next MPS receipt. Assume beginning inventory is 20 units. Week 1 MPS quantity equals 50 units. The next MPS receipt is in week 4. Customer orders are week 1, 15, week 2, 10, week 3, 8. First period ATP is 20 plus 50 minus 15 minus 10 minus 8. The result is 37 units. For a later MPS receipt, ATP is MPS quantity minus customer orders until the period before the next MPS receipt. Assume week 4 MPS quantity is 40 units. Customer orders are week 4, 12, week 5, 9. The next MPS receipt is in week 6. Week 4 ATP is 40 minus 12 minus 9. The result is 19 units. The company can potentially promise up to 19 additional units from that supply period. ATP should not be confused with inventory on hand. Inventory may already be committed to existing orders. Cumulative ATP allows unused availability from earlier periods to support later customer orders. Real-world company example. Amazon. When Amazon displays a delivery date, the commitment should reflect available inventory, incoming supply, fulfillment capacity, location, and transportation capability. Promising an order based only on total company inventory could be misleading when the inventory is already committed or located too far away. CPIM key takeaway. ATP determines how much uncommitted supply can be promised without violating existing commitments.
Topic 4. Schedule changes, nervousness, and MPS integrity. Schedule nervousness occurs when small changes create repeated changes throughout material and production plants. For example, moving one MPS quantity may cause MRP to cancel component orders, create new orders, reschedule supplier deliveries, change work center priorities, move purchase orders, increase or reduce inventory. When the schedule changes again shortly afterward, the system may reverse those actions. Excessive nervousness creates confusion, expediting, higher cost, supplier instability, employee frustration, and loss of trust in the planning system. The master scheduler should investigate the total impact before making a change. Important questions include: is the change inside a time fence? Are materials already committed? Is capacity available? Which suppliers are affected? Which customer orders are affected? Will another product be delayed? Does the change improve total performance? Firm planned orders may be used to protect selected plan orders from automatic system changes. However, excessive use of firm planned orders can make the plan unresponsive. The organization should also maintain accurate lead times, lot sizes, build of material, inventory records, routings, scrap and yield factors. Poor planning data can create apparent instability even when demand is stable. Real-world company example. Inditex and Zara.
Zara's operating model is designed to respond quickly to market information. However, responsiveness does not mean changing every activity without control. Design, production, distribution, stores, and inventory must remain coordinated. A change creates value only when the connected system can execute it. CPIM key takeaway. The MPS should respond to meaningful changes while resisting unnecessary adjustments that create schedule nervousness. Topic 5. Measuring master schedule performance. The organization should compare actual performance with the MPS. Possible measures include MPS schedule attainment, on-time completion, quantity completed, frequency of schedule changes, past due orders, number of expedites, MPS stability, customer service, inventory performance, capacity overloads. A basic schedule attainment calculation is schedule attainment equals quantity completed as scheduled divided by quantity scheduled, multiplied by 100. Suppose 1,000 units were scheduled for completion. Only 920 units were completed during the correct period. Schedule attainment equals 920 divided by 1,000 multiplied by 100. The result is 92%. However, a high percentage does not explain why the remaining units were missed. Possible causes include material shortage, equipment failure, quality problems, incorrect standards, labor shortage, unrealistic MPS, engineering change, supplier delay. Performance review should identify root causes. The company should not improve schedule attainment by creating an artificially easy schedule. The MPS should remain challenging but realistic. Real-world company example: Boeing. Boeing monitors the health of its production system through plans, processes, quality controls, workforce capability, and operational performance. For a complex product, missing one scheduled milestone may affect suppliers, downstream assembly, customer delivery, and cash flow. CPIM key takeaway. The MPS performance measurement should identify whether the schedule was realistic and whether execution achieved the approved plan. Let's summarize the 5 key lessons from Section E. First, control changes with time fences. Demand time fences, planning time fences, frozen zones, slushy zones, and liquid zones help protect schedule stability. Second, monitor projected available balance. PAB shows expected inventory after demand and scheduled production are considered, helping planners identify future shortages or excess inventory. Third, use available to promise correctly. ATP shows the uncommitted portion of inventory and scheduled production that can still be promised to customers. Fourth, avoid schedule nervousness. Frequent unnecessary MPS changes can create confusion, expediting, supplier instability, higher costs, and loss of trust in the planning system. Finally, measure master schedule performance. Schedule attainment, on-time completion, past due orders, expedites, customer service, inventory performance, and capacity overloads reveal whether the MPS is realistic and well executed. Section E shows that the master schedule must balance 2 forces: responsiveness to real change and stability for execution.
Section F. Material Requirements Planning. Section F Overview. Material Requirements Planning, commonly known as MRP, calculates which materials and components are required, how many are required, and when they are required. MRP is mainly used for dependent demand items. It converts the master schedule into time-phased material requirements. In this section, we will study 5 key topics. Topic 1. MRP purpose and inputs. MRP answers 3 main questions: what is required, how much is required, and when is it required. The 3 major MRP inputs are the master production schedule, bills of material, inventory records. The master production schedule provides the quantity and timing of parent item demand. The bill of material, commonly known as BOM, identifies which components are required to create the parent. Inventory records provide information such as on-hand balance, allocated quantity, scheduled receipts, lead time, lot size, scrap factor, yield factor, order status.
MRP output may include gross requirements, scheduled receipts, projected available balance, net requirements, planned order receipts, planned order releases, action messages. MRP requires accurate data. A wrong BOM quantity can create shortages. An incorrect inventory balance can create unnecessary orders or missing materials. An incorrect lead time can release an order too early or too late. An incorrect unit of measure may create a major quantity error. MRP is a planning system. It does not physically create materials. The organization must still release, execute, monitor, and control the orders. Real-world company example, Toyota. A vehicle requires thousands of components. The company should not independently forecast the number of every bolt, seat, and engine component used in production. Once the vehicle schedule and product structure are known, dependent component requirements can be calculated through BOM relationships. CPIM key takeaway. MRP converts the master schedule into time-phased dependent demand requirements using BOM and inventory information. Topic 2. Bills of material, explosion, and low-level coding. A bill of material describes the product structure. Consider this simple structure. Product P requires 2 units of component A, 1 unit of component B. Component A requires 3 units of component C. If the company plans to produce 100 units of product P, gross requirement for A equals 100 multiplied by 2, the result is 200 units. Gross requirement for B equals 100 multiplied by 1, the result is 100 units. Each A requires 3 units of C. Gross requirement for C equals 200 multiplied by 3, the result is 600 units. This process is called BOM explosion. The requirement moves from the parent through each lower level. Important BOM concepts include parent item, component item, single-level bill, indented bill, multi-level bill, phantom bill, planning bill, low-level code. The low-level code identifies the lowest level at which an item appears in any BOM. This ensures that all gross requirements for the item are collected before net requirements are calculated. An item may appear in several products and at several levels. MRP should not plan it separately at each level without combining the requirements. Engineering changes must be reflected accurately. If the BOM changes from 2 components to 3, but the system remains unchanged, shortages will occur. Real-world company example, BMW. A vehicle can be produced in many configurations. Digital product and production information helps connect engineering definitions with manufacturing requirements. Accurate product structures are essential because every configuration may create different component requirements. CPIM key takeaway. BOM explosion converts parent demand into component demand. Accurate product structures and low-level coding are essential for correct MRP calculations. Topic 3. The MRP time-phased record. The MRP record normally contains gross requirements, scheduled receipts, projected available balance, net requirements, planned order receipts, planned order releases, action messages. Consider this example. Component A has a beginning inventory of 50 units, a scheduled receipt of 30 units in week 3, safety stock of 10 units, lead time of 2 weeks, lot-for-lot ordering, a gross requirement of 200 units in week 5. Before week 5, available inventory equals 50 plus 30. The result is 80 units. To satisfy the gross requirement and retain 10 units of safety stock, net requirements equals gross requirements plus safety stock minus available inventory. Net requirements equals 200 plus 10 minus 80. The result is 130 units. Because the policy is lot for lot, the planned order receipt is 130 units in week 5. The lead time is 2 weeks. Therefore, the planned order release must be offset 2 weeks earlier in week 3. The sequence is, first, identify gross requirements. Second, add scheduled receipts. Third, calculate projected availability. Fourth, determine net requirements. Fifth, apply the lot sizing rule. Sixth, create the planned order receipt. Seventh, offset by lead time to determine the planned order release. Planners should distinguish planned orders from scheduled receipts. A planned order is a recommendation. A scheduled receipt comes from an order that has already been released. Real-world company example, Procter & Gamble. Producing consumer products requires ingredients, packaging materials, labels, cartons, and other components at specific times. Ordering every material when final production begins would be too late. Time-phased planning helps determine when each material order must be released so that it arrives before the production requirement. CPIM key takeaway. MRP calculates net requirements and offsets planned receipts by lead time to determine when orders must be released.
Topic 4. Lot sizing, safety stock, scrap, and yield. MRP applies lot sizing rules to net requirements. Lot for lot. Lot for lot orders exactly the net requirement. This minimizes excess inventory but may create frequent orders and setups. Fixed order quantity. A fixed order quantity uses a predefined quantity. If the fixed quantity is 100 units and net requirement is 130 units, the system may order 200 units. Order multiples. The order must be placed in multiples. If the multiple is 50 and the requirement is 120, the planned quantity becomes 150. Minimum order quantity. A supplier may require a minimum purchase. If the requirement is 40, but the supplier minimum is 100, the company may need to order 100 units. Safety stock protects against uncertainty. However, safety stock should not be used to hide poor data or unrealistic lead times. Scrap and yield factors adjust the planned quantity. Suppose the company needs 100 good units. Expected yield is 95%. Required input equals good units required divided by yield. Required input equals 100 divided by 0.95. The result is approximately 105.26. Because partial units cannot be produced, the company may plan 106 units. If scrap occurs at a specific BOM level, the adjustment should be applied at the correct level. Incorrect application can overstate requirements throughout the structure. Real-world company example. Dell. Electronic components may be purchased in supplier pack quantities or minimum order quantities. Some components may also have long lead times and technology obsolescence risk. Lot sizing decisions must therefore balance order cost, material availability, inventory, and obsolescence. CPIM key takeaway. Lot sizing and planning parameters convert net requirements into practical order quantities, but they also affect inventory, cost, and schedule responsiveness. Topic 5. Action messages and closed-loop MRP. MRP systems generate action messages when conditions require planner attention. Examples include release an order, expedite an order, de-expedite an order, increase quantity, decrease quantity, cancel an order, reschedule in, reschedule out. An action message is a recommendation. The planner should understand the cause and operational impact before acting. For example, expediting one order may delay another customer's order. MRP may be processed using regeneration. The complete plan is recalculated. This can ensure consistency but may require more processing and produce many changes. Net change. Only items affected by changes are recalculated. This can respond more quickly but requires reliable system logic. Bottom-up replanning. Communicates shortages or capacity problems from lower-level components back to higher-level plans. Closed-loop MRP connects material plans with the capacity, the master schedule, creation and change information from the bill of materials, inventory records, purchasing, production control, final assembly, and execution feedback. If capacity cannot support the material plan, the plan should be adjusted. Materials should not be released simply because MRP calculated them when the organization lacks the capacity to use them.
Firm planned orders can protect selected orders from automatic changes. However, they should be reviewed rather than forgotten. Real-world company example. Siemens. Integrated manufacturing planning systems connect products, bills of materials, resources, processes, schedules, and execution information. This supports faster responses when engineering, material, or capacity conditions change. The system becomes more valuable when planning receives feedback from actual operations. CPIM key takeaway. Closed-loop MRP connects material plans with capacity, execution, and feedback so that recommended orders remain realistic. Let's summarize the 5 key lessons from Section F. First, understand the purpose of MRP. Material requirements planning calculates what materials are needed, how many are needed, and when they are needed. Second, use accurate MRP inputs. The MPS, bills of materials, and inventory records must be accurate because errors in these inputs create shortages, excess inventory, or wrong order timing. Third, explode the bill of material correctly. Bill of material explosion converts parent item demand into lower-level component and raw material requirements. Fourth, calculate time-phased requirements. MRP uses gross requirements, scheduled receipts, projected available balance, net requirements, planned order receipts, and planned order releases. Finally, control lot sizing, safety stock, scrap, yield, and action messages. Planning parameters convert requirements into practical orders, while closed-loop MRP connects material plans with capacity, execution, and feedback. Section F shows that MRP is the bridge from the master schedule to detailed material planning, but it only works well when data, lead times, inventory records, and planning parameters are reliable. Section G. Capacity requirements planning, order promising, and final assembly scheduling. Section G Overview. Capacity requirements planning calculates the detailed capacity needed to execute planned and released orders. Order promising determines whether additional customer demand can be accepted. Final assembly scheduling converts available modules and actual customer orders into specific finished configurations. In this section, we will study 5 key topics. Topic 1. The purpose and inputs of capacity requirements planning. Capacity requirements planning, commonly known as CRP, determines the detailed capacity required by planned and released orders. CRP normally uses MRP planned order releases, open manufacturing orders, routings, work center information, setup times, run times, move times, queue times, efficiency, utilization. CRP is more detailed than RCCP. RCCP tests major resources against the MPS. CRP evaluates more detailed work center requirements generated by MRP. A routing identifies the operations required to produce an item. It may state operation sequence, work center, setup time, run time, move time, alternate resource, standard yield. Suppose an order requires a 2-hour setup and a runtime of 0.10 hours per unit. The order quantity is 200 units. Required standard hours equals setup time plus quantity multiplied by runtime. Required hours equal 2 plus 200 multiplied by 0.10. The result is 20 plus 2. The total is 22 standard hours. These hours should be placed in the periods when the operation is expected to occur. Real-world company example, BMW. Automotive production requires coordinated capacity across body, paint, assembly, inspection, and other operations. A total vehicle target is not enough. The organization must determine when specific work centers will receive the load generated by planned orders and product mix. CPIM key takeaway. CRP converts planned and released orders into detailed, time-phased work center requirements. Topic 2. Work center loading and capacity adjustment. A load report compares required capacity with available capacity. Suppose a work center has available capacity of 160 standard hours, planned order load of 110 hours, released order load of 70 hours. Total load equals 110 plus 70. The result is 180 hours. The overload is 180 minus 160. The result is 20 hours. Possible responses include overtime, additional shifts, alternate routing, subcontracting, moving orders, changing lot sizes, splitting orders, improving efficiency, adding employees, changing priorities. The planner should understand whether the overload is temporary or continuing. A one-period overload may be solved through overtime. A continuing overload may require investment or process redesign. Moving an order to an earlier period may solve one overload but create another. Capacity adjustments should therefore be evaluated across the planning horizon. Backward scheduling begins with the required completion date and schedules operations backward. Forward scheduling begins with the earliest available start date and schedules operations forward. Backward scheduling helps meet a required date. Forward scheduling helps determine the earliest possible completion date. Real-world company example. Aircraft manufacturing involves many connected work centers and major assemblies. When one critical area becomes overloaded, additional capacity elsewhere may not improve total output. The company must address the constrained resource through schedule, staffing, process, supplier, or capacity decisions. CPIM Key Takeaway. Work center overloads require operational decisions. Moving numbers in the system without changing resources, timing, or demand does not create capacity. Topic 3. Available to promise and capable to promise. ATP determines whether uncommitted scheduled supply is available. Capable to promise, commonly called CTP, goes further. CTP evaluates whether materials and capacity can support a new customer order. Suppose a customer requests 50 units for week 6. ATP shows only 20 uncommitted units. The organization could reject or delay the remaining 30. Alternatively, CTP may evaluate whether additional supply can be created. CTP may examine component availability, supplier lead times, work center capacity, alternate materials, alternate routings, overtime, subcontracting. Transportation. If the required materials and capacity can support 30 additional units by week 6, the organization may accept the full order. However, the promise should include the effect on existing commitments. Accepting a high-priority order may delay another order. Order promising decisions should be based on realistic supply information. The sales department should not promise a date simply because the customer requests it. The system should also account for product configuration, order quantity, location, inventory allocation, customer priority, lead time, capacity. Real-world company example. Amazon. Amazon's promised delivery dates depend on more than whether a product exists somewhere in the network. The commitment must consider inventory location, existing commitments, fulfillment capability, transportation options, and timing. This illustrates the principle behind realistic order promising. CPIM Key Takeaway. ATP checks uncommitted scheduled supply. CTP determines whether additional materials and capacity can create supply for a new customer order.
Topic 4. Final Assembly Scheduling. The Final Assembly Schedule, commonly known as the FAS, specifies the exact final products or configurations to be completed. It is especially important in assemble-to-order and configure-to-order environments. The MPS may schedule modules or subassemblies. The FAS uses actual customer orders to define the final combination. Suppose the MPS provides 100 base laptop systems. Actual customer orders require 40 standard configurations, 35 high memory configurations, 25 graphics configurations. The FAS assigns the 100 base systems to those specific final products. The schedule should confirm availability of base units, memory modules, graphics components, storage devices, packaging, labor, testing capacity.
The FAS is normally more detailed and closer to execution than the MPS. It should consider actual customer orders, order priorities, available modules, component availability, capacity, customer promise dates, and valid configurations. The organization should avoid completing final differentiation too early when customer demand remains uncertain. Postponement can delay final configuration until better demand information is available. Real-world company example, Dell. Dell's configured-to-order approach illustrates final assembly scheduling. Standard modules and components may be available before the customer order. After the customer selects the required configuration, final assembly, software loading, testing, packaging, and shipment can be scheduled for that order. CPIM key takeaway. The FAS converts actual customer orders and available modules into specific finished products. Topic 5. Maintaining the FAS and monitoring performance. The FAS must be maintained as conditions change. Important changes may include customer priority, order quantity, configuration, material availability, capacity, supplier delivery, engineering changes, backlog, quality problems. The final assembly scheduler should understand which orders are already committed and which can still be changed. Changes inside a short time fence may disrupt material staging, labor assignments, testing, packaging, or customer delivery. The scheduler should monitor FAS attainment, order completion, past due orders, material shortages, configuration errors, customer promise performance, backlog, capacity usage, and the rate and mix of final assembly output. The FAS should remain connected to the MPS. Final assembly should not consume more modules than the MPS and material plan provide. If demand for one configuration increases, available modules may need to be reallocated. The organization should also monitor internal and external supply. A shortage from an external supplier may prevent final configuration even when internal capacity is available. Real-world company example, BMW. Customers may select different engines, interiors, equipment packages, and options. The final production sequence must ensure that the correct components reach the correct vehicle at the correct time. Changes must be carefully controlled because a configuration error affects quality, customer satisfaction, materials, and delivery. CPIM key takeaway. The FAS should remain synchronized with customer orders, modules, materials, capacity, supplier deliveries, configuration rules, and the MPS. Let's summarize the 5 key lessons from Section G. First, use CRP for detailed capacity planning. Capacity requirements planning converts planned and release orders into time-phased work center loads. Second, analyze work center loading. Load reports compare required capacity with available capacity and help identify overloads, underloads, and required adjustments. Third, separate ATP from CTP. ATP checks uncommitted scheduled supply, while capable to promise checks whether extra materials and capacity can support a new customer order. Fourth, use final assembly scheduling for exact configurations. The FAS converts available modules and actual customer orders into specific finished products. Finally, maintain FAS performance. The final assembly schedule must remain synchronized with customer orders, modules, materials, capacity, supplier deliveries, configuration rules, and the MPS. Section G shows that customer promises must be realistic. A company should not accept orders based only on hope, sales pressure, or total inventory. It must confirm actual supply, capacity, and configuration feasibility. Section H. Changes and supply disruptions. Section H Overview. Internal supply plans operate in a changing environment. Demand may increase or decrease. Machines may fail. Employees may be unavailable. Materials may be delayed. Quality problems may occur. Customer priorities may change. Organizations must respond without losing control of the total plan. In this section, we will study 5 key topics. Topic 1. Reprioritizing orders within time fences. When supply or demand changes, management may need to reprioritize orders. Possible priority factors include customer commitment, contractual obligation, strategic customer, product margin, safety requirement, medical or essential use, material availability, order age, customer impact. Time fences should still be respected. Changing an order inside the frozen zone may require senior approval because materials and capacity are already committed. Reprioritization should examine the total impact. Expediting one order may delay another customer. Increase overtime. Create premium transportation. Interrupt a production sequence. Increase changeovers. Create material shortages. The organization should have clear rules for priority decisions. Without agreed policies, priorities may be determined by the most influential salesperson or the loudest customer. The new priority should be communicated to production, purchasing, suppliers, customer service, logistics, finance, affected customers. Real-world company example: Toyota. When a critical component becomes limited, Toyota may need to determine which products, facilities, or customer commitments receive available supply. The decision should consider the impact across the production network rather than one department alone. CPIM key takeaway: order reprioritization should follow approved rules and consider the effect on all customers, resources, materials, and existing commitments. Topic 2. Adjusting planning parameters. Planning parameters may need to change when conditions change. Common parameters include lead time, lot size, safety stock, order quantity, replenishment quantity, cycle time, yield, scrap factor, minimum order quantity, capacity rate. The organization should not assume that planning parameters remain correct forever. For example, a supplier lead time may increase from 4 weeks to 7 weeks. If the system still uses 4 weeks, planned orders will be released too late. A product entering decline may require smaller lot sizes to reduce obsolescence. A product experiencing greater uncertainty may require a temporary safety stock adjustment. Changes to parameters should be controlled. The company should record the reason for change, effective date, owner, expected result, and review date. Temporary changes should not become permanent simply because nobody reviews them. Changing a parameter can create consequences throughout the plan. Increasing safety stock may generate new orders. Reducing lead time may delay order releases. Increasing lot size may create excess inventory. Real-world company example: Amazon. Demand and capacity requirements can change significantly during peak shopping periods. Inventory placement, staffing, facility usage, transportation, and replenishment parameters may need to reflect the different operating conditions. Using average period assumptions during a major peak could produce inadequate plans. CPIM key takeaway: planning parameters should reflect current conditions, but every change should be controlled, justified, communicated, and reviewed. Topic 3. What-if analysis, simulation, machine learning, and AI. What-if analysis evaluates the possible result of a proposed change. Examples include: what if demand increases by 20%? What if a supplier is unavailable for 6 weeks? What if a machine fails? What if overtime is added? What if production moves to another facility? What if the product mix changes? Simulation may test several connected variables. It may evaluate capacity, inventory, lead time, queues, material availability, customer service, cost. Advanced analytics may use machine learning and AI to identify patterns and evaluate alternatives. However, models are not perfect. Management should understand data assumptions, model limitations, uncertainty, decision risks, and human judgment. Human judgment remains important. The organization should compare alternatives using agreed criteria. These may include customer service, recovery time, cost, inventory, revenue, margin, risk, quality, employee impact, sustainability. The purpose is not to produce the most complicated model. The purpose is to improve the decision. Real-world company example. UPS. UPS uses dynamic route optimization technology that can recalculate delivery routes as traffic, pickup commitments, and delivery conditions change. This illustrates how analytics can evaluate changing operational conditions and recommend a revised plan. CPIM key takeaway. Analytics and simulation help management evaluate trade-offs before changing the supply plan, but decisions still require reliable data and business judgment.
Topic 4. Redundancy and strategic buffers. Redundancy means maintaining additional resources or alternatives. Examples include backup equipment, alternative production lines, cross-trained employees, alternative routings, secondary facilities, multiple suppliers, backup information systems. Buffers may include inventory, capacity, time. The organization should decide where buffers provide the greatest protection. Holding safety stock for every item may create excessive cost. A buffer is most valuable when it protects a bottleneck, a long lead material, a critical customer requirement, a single source dependency, a high-impact risk. A capacity buffer may allow the organization to respond to unexpected demand or equipment failure. A time buffer may protect a customer date. An inventory buffer may protect production from supplier variability. Redundancy and buffers reduce some risks but create costs. Management should compare the cost of protection with the possible impact of disruption. Real-world company example, Amazon. Amazon's network includes different facility types, inventory locations, technologies, transportation capabilities, and facilities that can support seasonal peaks. This network flexibility provides alternatives when demand or operating conditions change. CPIM key takeaway. Buffers and redundancy should be placed strategically. Maximum redundancy is expensive, while no redundancy can leave the organization vulnerable to a single failure. Topic 5. Business continuity and disruption recovery. A business continuity plan explains how the organization will continue or restore critical activities after a disruption. The plan may address natural disasters, cyber attacks, power failures, equipment breakdown, fire, labor shortages, supplier failure, transportation interruption, quality incidents, political disruption. Important elements include critical process identification, emergency responsibilities, communication procedures, backup systems, alternative facilities, supplier contacts, data recovery, inventory protection, customer communication, recovery priorities, testing and training. Recovery time objective identifies how quickly a process should be restored. Recovery point objective identifies how much data loss is acceptable. A plan that has never been tested may fail during a real emergency. Organizations should conduct simulations, tabletop exercises, supplier reviews, emergency drills, system recovery tests. After the disruption, the company should review what happened, which assumptions were incorrect, which actions worked, which information was missing, and which capabilities should be improved. Business continuity is not only an emergency document. It should influence daily decisions about visibility, buffers, suppliers, systems, employees, and facilities. Real-world company example, Toyota. After major disasters affected production and supply networks, Toyota developed stronger supply chain visibility and continuity practices. Its RESCU supply chain database was designed to improve information about important items and suppliers during a crisis. Toyota also conducts continuity activities and training with suppliers. CPIM key takeaway. Business continuity planning should identify critical operations, responsibilities, alternatives, communication, and recovery actions before disruption occurs. Let's summarize the 5 key lessons from Section H. First, reprioritize orders carefully. When supply or demand changes, order priorities should follow approved rules and consider customer commitments, contracts, margins, strategic importance, materials, and total system impact.
Second, adjust planning parameters when conditions change. Lead times, lot sizes, safety stock, yield, scrap, order quantities, and capacity rates must reflect current reality, not outdated assumptions. Third, use what-if analysis and simulation. Analytics, AI, machine learning, and simulation can help compare alternatives before changing supply plans. Fourth, protect the system with strategic buffers and redundancy. Inventory, capacity, time buffers, backup suppliers, alternate routings, cross-trained employees, and backup systems should be placed where failure would create the greatest impact. Finally, prepare business continuity and recovery plans. Organizations must identify critical processes, emergency responsibilities, communication methods, backup systems, recovery priorities, and disruption response actions before problems happen. Section H shows that internal supply planning is not static. Strong organizations prepare for change, disruption, uncertainty, and recovery before the emergency arrives. External supply and key support functions. We will examine suppliers and procurement, purchasing and maintenance, risk management, sustainability strategies, waste hierarchy, and reverse logistics. Remember to review the topics using the CPIM 9.0 Full Learning Bundle. Test your understanding with the 6,200 plus MCQ Practice Bundle, and revise the important terms using the 1,800 Flashcards Bundle. The download link for all three bundles is available in the video description. Don't forget to like and subscribe to the Simple Understanding YouTube channel and activate notifications so you do not miss any lesson. Share this course with anyone preparing for the CPIM exam. See you next video.